Sasank Mule is going to give the talk, please.
Thank you, Jakob. So uh, this is going to be a talk about this proof system polynomial calculus and some of the new work that has been going on recently. So more traditionally, work has focused on Boolean basis, or basically when variables take values 0 or 1. But here in our work and prior work, we have been investigating when uh, values are taken which are not 0 1. It could be like plus minus 1, or it could be from some other finite field. So uh, I'll get into why that is interesting. So, and this is a joint work with Yogesh and Meena. Okay. And so before we begin, here is a quick overview of what is this polynomial calculus proof system. So polynomial calculus is a proof system where so we are given, let's say, a tautology, a true Boolean formula, right? And we want to certify that it is indeed a tautology, or usually we are given the negation of that as an unsatisfiable formula, and we want to kind of come up with a proof of a contradiction from this formula. And for that, we have many proof systems. So you might have seen systems like resolution and cutting planes. And so polynomial calculus is one such proof system with an algebraic flavor, where um, your unsatisfiable formula, you encode it as a system of polynomial equations over some field, right? And so given this system of polynomial equations, polynomial calculus proof is kind of a derivation system where you can derive new polynomials from these initial axioms through these two rules, where you can, given two polynomials, you can take any linear combination of these polynomials, and given a polynomial, you can multiply by a variable and derive a new polynomial. Okay. So these two are sort of sound rules, which so given that certain polynomials are 0, they always derive new polynomials that are also 0. And you want to ultimately derive the polynomial 1, so that you get the equation 1 equal to 0, which is a contradiction. And that tells you that the original formula was unsatisfiable, or the original system of polynomials is unsatisfiable. Okay. So basically, we are kind of working in the ideal generated by these polynomials, and we are kind of deriving new uh, polynomials step by step. Okay. um, so um, uh, since this proof system was introduced in maybe like 93 or 94, so people have done a lot of work on proving lower bounds for this proof system. So in the sense that which formulae require large proofs in this to refute in this proof system. So so the key tool used for this is what we call this size degree trade-off. So basically that says that so if you can prove a strong enough degree lower bound on the proof, on a proof of on any proof of a formula, then you automatically also get size lower bounds, that uh, the size also has to be large. So so one way to state it is, if you have a small size proof of size s, then you also have a small degree proof of like square root n log s. So the contrapositive would be if you prove a linear degree lower bound, in the sense that you show that some formula in n variables requires degree omega n, let's say, right? Then you also end up getting exponential size lower bounds for the same formula. Okay. So let me quickly go over how this works, because this is going to be useful in later discussion. Um, uh, so the main idea is that so within this proof system PC, you can branch on the value of a variable xi. So let's say I want to come up with a proof of a formula f of degree d. then what you can actually do is you can simplify the problem into these two parts, two branches, where you pick some variable xi, any arbitrary variable, and you come up with a proof of degree d minus 1 of this formula f at x equal to 0, right? So you're kind of branching on x, and you're saying, okay, let me set x equal to 0, let me solve that problem, right? So let me come up with a proof for that case, and then let me again set x equal to 1, and let me come up with a proof for that case. And so if in one of the branches if you are able to lower the degree, right? So let's say by setting x equal to 0, you're able to come up with a small degree proof, a degree d minus 1 proof, and maybe the other branch you still come up with a degree d proof. Then within PC, you can combine these two proofs into a proof of the original formula of degree d. Okay, so we are simply again saying, okay, set x equal to 0, come up with maybe a smaller degree proof, set x equal to 1, and you can combine those two into a degree d proof. So how does this trade-off, how do we show this trade-off? So we say, okay, suppose you give me a small sized PC proof. Let a fat term be of degree more than d, right? So these are our target terms, in the sense that, so given a small size proof, we want to eliminate all these high degree terms or these fat terms. And what we observe is that just by an averaging argument, there is a variable that appears in a d over n fraction of these fat terms, right? Because each term contains at least d variables, and there are n variables in total, so there is a variable appearing in a d over n fraction. So what do? We simply branch on this variable which is appearing a lot, what we call a popular variable. So now when we set this variable to 0, we observe that, okay, so that branch is of smaller size now. It has fewer fat terms, right? So because this was appearing a lot in the proof, so by setting it to 0, we shrunk the proof by some factor. Okay, and then the other branch, we are not able to shrink the proof maybe, so we just leave it as it is. And then by induction, we say that, okay, this branch has a proof of degree d minus 1 because it has fewer fat terms, right? It's a smaller sized proof, and this branch has a proof of degree d. Um, and then we can combine these two into a proof of degree d of the original formula. Okay, so so this is like a rough sketch of how size and degree are connected for these proofs. Okay, but this is also the starting point of our work here, or discussion here, because so we should observe is that this proof crucially relies on the fact that the values are 0 or 1. So in particular, it relies on the fact that setting this x to 0 kills some terms in the proof, right? So it if there is a term, uh, a monomial in the proof, you set a variable in it to 0, that term disappears, right? So this is very much dependent on this 0 1 valued variables. Okay, so and so this connection has been used to prove some lower bounds. So I'm just stating some of the earlier works, but there have been many works later on. So again, using this generic connection, people proved degree lower bounds. So here are just one of the first two degree lower bounds, and so. But as I said, uh, uh, this degree and size connection is only very specific to 0 1 variables. So so then once there was enough progress in this case of 0 1 variables, and we had enough size lower bounds, then we started asking, okay, can we actually go beyond that, and can we prove lower bounds for systems that are stronger than PC? And so in fact, one of the reasons that PC was introduced was lower bounds for this more complex system AC0 P Frege, because uh, so this system is this system of constant depth circuits with modular p gates. So basically you have constant depth circuits, like circuits which have and or gates with unbounded fan in and constant depth, right? And additionally you can have, let's say, mod p gates, or let's say parity gates, for instance. And so AC0P Frege denotes the proof system which whose lines are these AC0P circuits, right? Uh, so AC0P Frege is a proof system that naturally manipulates circuits of these constant depth modular P circuits. Okay, and so this has been a long-standing open problem in proof complexity, and it's interesting because uh, we have AC0P circuit lower bounds, right? So if you just forget about proofs and you just ask me, is there a function, Boolean function, that requires large uh, circuit complexity, AC0P circuit complexity, then there are lower bounds due to Rasburov. So there and Smolensky. So for instance, a parity function is hard for AC0P where P is not equal to 2, right? Um, so we have good circuit lower bounds for these circuits, and they have been proved, I think, in the 80s or so. So for a long time we had circuit lower bounds for this class, but we haven't been able to show proof lower bounds. So where proofs using these circuits, we are not able to prove lower bounds. So and so the proof of circuit lower bounds for these circuits went through some kind of algebraic reasoning. So it goes through this approximating polynomials. So basically you show that for instance a parity gate cannot be approximated by f3 polynomials, low degree f3 polynomials, but these circuits can be approximated well by low degree f3 polynomials. So that's how the circuit lower bounds go, but we cannot we don't really know how to transport it into the proof complexity world, because it's difficult to make a notion of approximate proofs or proofs with approximate polynomials. Okay, so then people started looking at more algebraic proof systems or algebraic reasoning, uh, so proofs using algebraic reasoning, and thought maybe, okay, so if we prove lower bounds for these algebraic systems, it might give some insight to on how to attack this bigger problem. Okay, um, but the state of affairs currently, or let's say a few until a few years ago, was that uh, we had lower bounds for PC, but they did not translate to lower bounds for AC0 P Frege due to a few reasons. Basically, what are those reasons? So, like I said, these lower bounds are mainly over 0, 1 valued variables, right? And that is very crucial in these size degree trade-offs. And you can just simply observe that this kind of approach where we are restricting values to 0 or 1 doesn't work when mod p gates are in the picture. Like, so for example, if you have a big parity gate, you set variables to 0 or 1, nothing is going to happen to the parity gate. It's not going to disappear, unlike an AND gate or an OR gate, right? So an AND gate, OR gate can be set to true or false using such restrictions, but parity is untouched basically. And so so then the idea was to look at maybe PC like proof systems that are closer to AC0 P Frege. So okay, so because that's seems like a more approachable goal. Okay, um, so Uh, so one way to add strength to these systems, is this PC, for example, is to allow PC to branch on not a single variable, but some condition f x1 to xn, right? So in general, if PC, we would do it naively in PC, then it would branch on all the variables underlying this condition, and that would be an exponential blow up. But what we do in this new system is we introduce what we call extension variables. So where we say, okay, set y equal to some function of the original variables, right? Some non-trivial function. So now y is a new variable. So you can use y in the proof as if it's a variable given to you. So in a sense, we are saying that you don't need to expand out f each time, right? So you can use y in the proof, and whenever you need to do some computation, you can expand it into f, do computation, and close it back, and uh, continue with the proof. So that saves a lot of proof size, right? So uh, then people started looking at this new system where which is PC with constant depth extension variables, where basically that system is you have rules of PC, plus you can introduce new variables. So you can introduce a variable that is a sum of existing variables, or a product of sums, or sums of product of sums, and so on. And so this is one natural extension of PC, which is somewhat close to maybe AC0 P-Frege. And so the question was, how strong is this system? And so what people found out fairly quickly, that was that this system is in fact pretty strong, in even if you take constant depth extension variables. So you take only constant levels of extension variables. So let's say some product of sum of product of sum. So that way constantly many levels. So Grigoriev and Hirsch actually were the first to talk about this system, and they showed already that this system can simulate at a constant depth. It can simulate AC0 P-Frege, and we were able to show that this system actually can simulate other semi-algebraic systems also, which was somewhat surprising, but again at a constant depth. So what we ended up realizing was that this system is pretty strong even at constant depth, and it seems more out of reach than AC0 P-Frege, right? So then what is so again? So we want to look at maybe concretely the simplest system for which we can do something new, right? We can go beyond this 0 1 regime. So, and the simplest such system is actually if you just consider instead of 0 1, you consider plus minus 1 valued variables, right? And already here this size degree approach doesn't work. And moreover, there is also a counter example for the size degree connection, that there are these Seitin tautologies, or a system of F2 linear equations, which require large degree but have small sized proof over plus minus 1. So there cannot be a generic size degree connection because there is an example with a small size proof but requires a large degree. Okay. Uh, and you can also view it as a morally as a weak subsystem of AC02 Frege with this small change of basis. Like, so you can introduce new extension variables which just change the basis using this small 2x minus 1 this transformation, and uh, so it is kind of a weak subsystem of AC02 Frege. Okay, so and already we were stuck here. So, and the state was that PC lower bounds were not even robust to this small change of basis, and and so then the first breakthrough actually came due to Sokolov in 2020, where he showed how to obtain lower bounds for this system PC over the plus minus 1 basis. Okay, so sorry, how much time do I have? 7 8 minutes. Okay. Um, okay, so I had some technical stuff for this lower one, but I'm going to gloss over it. So basically, he introduced these two new notions called quadratic degree and split, where he showed that using this new operation split, which so I'm not going to get into. He by applying this operation, it works similar to setting variables to 0 or 1 in the 0 1 world, and so that acts similar in this plus minus one world. And instead of degree, he introduced this new measure called quadratic degree, which is actually, it's kind of the symmetric difference between two terms. That's what it basically is. Like, so if you have two terms t1, t2, which variables are not common to both of them, both of those terms. So that is what quadratic degree is. And so, but anyway, so he introduced this new operation split, and he introduced this new measure quadratic degree, and he showed that okay, so by applying split, you can reduce quadratic degree of the proof, even if the usual degree is not reduced. And then once quadratic degree is low, he showed how to convert that proof into a low usual degree proof. So then indirectly we get uh, a size quadratic, like a size degree trade-off, but only for specific formulae where which are robust to this split operation. Okay, so so it's kind of an indirect way using this new operation and this new notion of quadratic degree, but it was essentially a size degree trade-off, but for some specific formulae. Okay, um, and so basically his result was lower bounds for PC over plus minus one basis. So so I'm just going to skip this technical part and jump to our first result, which is basically an improvement of Sokolov's result. So so basically we show a general lifting kind of result where we show that if a formula F requires PC degree D to refute, right? Then if you compose it with the indexing gadget, then this formula requires exponential size in D to refute in PC plus minus one, right? So uh, this is what we show as our first result. And so Sokolov had a similar lifting result, but he stated it only for a different system SOS, and which also implies a result for PC, but only over the real field. And the result also quantitatively it is slightly weaker, or it's of the form d square over n, so it doesn't give meaningful bounds for low degree, degree lower bound. So if d is around root n, it doesn't give anything. But our result works over any field, and it gives lower bounds for any super constant d. So if you have any super constant degree lower bound, you get an sort of an exponential uh, or a super polynomial size lower bound. Okay. Uh, so so again, I'm not going to go into the technical details of this of this proof. It's a fairly simple proof, but it's very much inspired by this result of Cross Pudlak for which who proved a similar result over just polynomials for Fourier sparsity of polynomials. So again, it's kind of like a circuit lower bound or a result which we transported into the proof world. Okay, and uh, so then I mentioned the extension variables. So then after Sokolov's result, there was another result where so we were able to show lower bounds for PC with some weak extension variables, because as I mentioned, for general extension variables, PC becomes very strong. So we were able to show a CNF. So in an earlier result, which with subquadratic many extension variables, right? So if you are restricted to only little of n squared many extensions, and each extension depends on only order log n original variables. So for this restricted setting, we were able to show lower bounds, right? So again, it's a only if you like n square many extensions, and each extension is also very local. It depends on only log n variables. So uh, we were able to show in earlier work lower bounds for this. And so our second result here is an improvement over this result, where where we improved the parameters of this earlier result, where we show lower bounds for a PC with extension variables, where again, so we are only able to deal with a subquadratic number of extensions, but uh, here the each extension can depend on more variables. So from order log n, we are able to improve it to order n1 minus epsilon, so very close to depending on all the variables. But there is this additional little caveat that the extension variable has to be polynomial size, so it cannot be a very huge. So when written as a polynomial, it cannot be too huge. It has to be a polynomial sized polynomial, basically. Number of monomials has to be poly size, and but with poly size, it can depend on very close to all the variables, and we still show lower bounds for PC with these kind of extensions. But again, there is just another little thing I have to mention, that the earlier result was for a CNF formula, where it's a Boolean formula. But here this is it's for some set of polynomials, which is a simple set of polynomials over this field f, but it's not a CNF formula. Okay, it's just some set of polynomials. So I think I'm out of time. Uh, yeah. So again, I had some technical stuff for this, but which I'm going to gloss over. So I'll just mention. Okay, the tautology for our lower bound is basically due to Rasborov in his original degree lower bound for PC, where he modified the pigeonhole principle tautology uh, to make it sort of more compact, where so usually a pigeonhole principle maps pigeons to holes, right? So it says you have, say, n+1 pigeons and n holes. uh, you want to say that each pigeon gets its own hole, but here we just so Rajparov modified the tautology to encode each pigeon not with a individual variable, but with a term. So instead of pigeons being independent variables, they are treated as subsets of a universe. So each pigeon is some R-sized subset of this universe 1 to m, and then each of these subsets we map to some smaller number of holes. Okay, so again, I have some uh, more technical stuff where which I don't have time for, but the axioms look something like this. So this product term denotes one pigeon, where it's a subset. The subset I of the universe denotes the ith pigeon, and we are saying that this product, it denotes that this pigeon goes to the jth hole, and so we have axioms saying each pigeon has to go to some hole, and no two pigeons go to the same hole, and so on. Okay. Um, so yeah, I'm going to skip over this all this technical part. Maybe uh, so this is just a sketch. I mean, this might be a lot, but it's very similar to, if you look at it's just a slightly more complicated version of what we did over 0, 1, where we just pick a variable that occurs a lot in the proof, and we do some sort of case analysis, right? So we say if the variable can take a value 0, then we just do as before, we just set it to 0. But if it doesn't, it's not able to take a value 0, then we use this framework of Sokolov, where he used this split operator, and he used quadratic degree. So if it's not able to take a value 0, we use that framework to reduce quadratic degree. And either way, we overall we end up reducing the quadratic degree of the proof, and we repeat this process until the proof is of low quadratic degree. And then finally we use again Sokolov's argument of converting to low degree, and we end up contradicting known degree lower bounds. Okay, so again, sorry for the quick sketch, but it is yeah, basically very similar to the Boolean case, but with this extra machinery split and quadratic degree. Okay. So yeah, I'm just going to, yeah, okay. Okay, thank you.
So we can take maybe 1 or 2 questions while the next speaker sets up. So how it seems like for which of these results can I plug in a CNF formula to get a lower bound?
The first result you can plug in, like where we prove or plus minus one this kind of lifting. But for the second result, it's that algebraic version of PHP.
And getting from this algebraic version to something in conjunctive normal form, that would like require a lot of extra. Is there any hope for pushing this to CNF?
To CNF, yeah, it seems difficult. Yeah. Right now, I don't think we have any good ideas to.
Other questions? Let's thank Sasank again.
Me. So I put that thing. Zoom. I'm going to. Yeah, I'm not sure I will.
So the next
This one.
talk was the slides were flashing by and then they disappeared, and now they're back again. So we're going to hear about compilation to decision DNF.
Yep.
By Alexis de Colnay. So please.
Okay. Yeah. So I'm going to talk about knowledge compilation. So that's some work that I've done that I find quite hard to explain. So it's not going to be a technique, really technical. I mostly try to explain what I'm trying to do and why I find it interesting. But there will be no proof. I invite you to read the paper if you want to find all the gory details of the proof. So no, I always have one slide on knowledge compilation. So just to explain roughly what's happening here. So the key notion is here is the notion of language. And that's not language in the complexity theory sense. For us, for me, a language is just a class of representations. Like the language of the CNF language is just the class of all CNF formulas. Right? And when you compile, it means that you go from one language to another. So you take a CNF, input. So that would be something like to take CNF formula and you try to find another representation, usually some kind of Boolean circuits that represents the same function as the CNF, right? Okay, so I will use to start this DDNNF circuit. So I'm not going to use the definition right now, but basically, yeah, compilation is just you take a CNF and you try to obtain these circuits with some specific properties. And why do you want to compile? Because, well, the properties of these circuits are such that it enables you to do many. It unlocks some operations, basically, like things like doing model counting on the CNF is hard, but on that kind of object, thanks to the property of the circuit, it will be linear time. All right. Well, of course, in practice, what you would obtain, so you can't really go from a CNF formula where model counting is sharply hard to something where it's linear time that easily. So often the size of what you obtain, the compile form, so whatever that thing is, will explode. And you can't really, so it's provable that for some CNF, you would just have something of exponential size. So it's of tremendous importance in knowledge compilation to study the different languages in terms of spatial efficiency. So there is this notion that it was introduced more than 20 years ago of succinctness, where you say that, okay, you have two classes of representation, two language, L1 and L2, and you say that L1 is at least as succinct as L2 when you have the following. So whenever I have a representation in L2, right, some kind of circuits, I can always find another representation in L1, which is which represents the same function, but which is whose size is polynomially related. So you don't lose that much space by going from L2 to L1. That's what this is saying here. That's the succinctness. And just to give an example that will allow me to introduce the kind of circuits that I've studied in this paper, so the decision DNNF. So I'm going to just give you this succinctness relation between the DDNNF circuits and the decision DNNF. So, and now I need to introduce what DDNNF are. So a DDNNF circuit, it's a Boolean circuit like this, where you have only two kinds of gates. You have the OR gate and you have the AND gate. The NOT gate you don't have. You push them down to the literals. And you need some properties on your gates. The AND gates have to be decomposable, which means that whenever you have an AND gate, the two children, they are not allowed to share variables. So this one, on one side you have x1, x4, on the other side you have x3, x5. So this joint, it's a decomposable AND gate. And you need this for all your AND gates. For the OR gates, the property you want is what's called determinism. And so we'll just assume that all the OR gates have Fanin 2. And determinism is saying that, well, when I look at the two children of the OR gate, they cannot be satisfied by the same assignment simultaneously. If you have an assignment that results in one children assigning to true, the other, evaluating to true, the other one must evaluate to false, and vice versa. And these two properties alone allow you to have to do model counting in linear time. Good. Now, it turns out that in practice, how do you construct these things? Well, you create deterministic OR gates by just looking at a variable and deciding of its value. So, like if you look at this OR gate here, why is it deterministic? Because for the first child to evaluate to true, you need x1 to be set to true. For the second child to evaluate to true, you need x1 to be set to false. So this OR gate is just controlled by a single variable. And so you write it like this, but you can write it like this. When x1 is set to true, I want that subcircuit to be satisfied. When x1 is set to false, I want that one to be satisfied. And when you only have decomposable AND gates and decision node of that form, you obtain these decision DNNF circuits. And that's what you obtain in practice. You don't really obtain these things. You obtain this kind of thing. Okay. And so what is known is that, all right, when I have a decision DNF circuit, I can always rewrite it, massage it into a DDNF circuit. It's fine. It's a linear time operation, easy. However, the other direction is not true. So when you have a DDNF circuit, you cannot you have some functions that have DDNF circuits of polynomial size, but when you try to find the decision one, DNF circuit, then the size explodes. So what it means is that when you look at all the good DDNF circuits, so this one of polynomial size, yeah, the good decision DNF circuit, you don't have as many good polynomial size decision DNF circuit as DDNF circuits. So we will have smaller representation in this language. Good. Now switching to compilation algorithm. All right, so this compilation language, these classes of representation we actually want to compile, to transform a CNF to this language in practice. They are not some theoretical object, right? And so we have algorithms that do this. So I put some example here. So the most well-known C2D, D4, that should be D sharp, not sharp-sat. And sharp-sat TD, not really a compilation algorithm, but like there is this paper KR 2023 by Kiesel and Thomas Eiter that shows that, yeah, you can basically see this as a compilation algorithm. It's fine. And so the way I like to see compilation algorithm is that if you don't have any randomness in your algorithm, it's basically a mapping from the input language to the output language. And all these algorithms are usually advertised as going from transforming CNF into DDNNF. At least for C2D, when you look at 20 years ago when it was introduced, that's how it was described. And then people realize, oh no, in fact, you're actually always going to decision DNNF. So you're finding things that are much larger than if you were actually able to compile to create DDNF circuits. And I would argue that you can go even one step further, because it is, for me, a bit weird to just, I mean, at that point, you don't really, you don't have a really smaller language that decision DNNF. They all create these circuits, but they all have different strengths. So what I'm interested in is basically looking at the compilation algorithm and at looking at what they are actually able to create. They don't just go in DDNF; they go to decision DNNF. But but they don't even go really all of them to the full. They cannot find all decision DNNF. Each of them can only find a small fraction of all possible decision DNNF, and each of them can find different small decision DNNF. Some of them won't be able to find, like C2D is probably not able to find decision DNF that are as small as the one that D4 can find, and vice versa. You have examples like this. And that's how I want to compare the compilation algorithm. Rather than empirically, when you have a bunch of benchmark, I want to, what I'm trying to do is find examples of CNF so that you can prove that for some compilation algorithm, some compilation algorithm will return decision DNF that is always exponential size, but some other will return polynomial size, and vice versa for other examples. What I've done in the paper is that I've looked at the top-down compilation algorithm. So all these 4 algorithms are top-down. So they all follow the same model, which is this exhaustive DPLL. And yeah, it's all follow this exhaustive DPLL, but there are some differences, and that's by analyzing these differences and creating general model that I can prove some separation result between the algorithm. So first, I'm going to review this a bit, because I actually need to review it exhaustive DPLL a little. So so that's this compiled procedure. So you have 2 inputs, which are the CNF you're trying to compile, and a set of variables. The set of variable S is a set of variables you have to assign in priority. Okay. Initially, this set is empty, and then you will have to create it. But before you choose which variable you have to assign, you have to do a bunch of things on your CNF. The first thing is you can do some kind of processing, like this can be unit propagation, this can be backbone identification, vivification, closed subsumption, that kind of stuff. What you would obtain is that you will modify your CNF-F. So F here is not the same as that one. You have modified it a little, and maybe you will have learned some literals that I put in this toe here. Okay. Then you have every time you call the compiler, what's happening is that you will look at if the formula is unsat. So you have a sat solver or sat oracle, even if you want, and if it's unsat, then you just return 0. And also, if you have emptied the CNF from all its clause, then you return 1. Okay. Assuming you've got past these steps, then the thing you do is you look at the cache, because this compile algorithm you will call it several times, and maybe the formula that you're trying to compile, possibly you found it in the past already, and then you look at your cache, and if you have a cache hit, then you just return whatever you have already constructed for the formula. You don't repeat the construction. That's quite standard. Okay, now it's becoming a bit more interesting. Before you even try to assign variable, you will want to see if your formula is decomposable. So if you can partition your formula into a bunch of subformulas that share no variables, you're going to create this decomposable AND gate, right? And the way I see it done in practice, by the way, this is inspired from how D4 is described in the original paper. So you will compile each subformula independently, each component of the formula independently, and you reset the set of variables to assign to 0. So even if you had still some variable to assign in priority, once you said that, oh yeah, I can decompose, then you reset them. You reset this set of variables to 0. And only after, and only if you have not if you found that your formula is a single component, it's one big formula all connected, you have no decomposability, then you can start assigning variables. If you already have some variables to assign from your set, then you just select one in any way you want and you assign it. Otherwise, you have to select the variables to assign priority. And so that's where it differs a little from exhaustive DPLS. So in practice, the strategy, it seems to me, is you try to split you select variables so as to split your CNF formula as quickly as possible. So your CNF will be one component, and you will try to find a subset of the variables so that whichever way you assign them, you will split your formula into disjoint component, and you will be able to create these decomposable AND gates. And you do this because that's when you create these things that you actually win space. All right. And once you found this set of variables to assign, which is called a cut set, I mean, that's not my term, but we'll call it a cut set, then you have to select a variable from the cut set. And then with variable you select, you assign it to false, you obtain a subproblem, or you assign it to true, you obtain another subproblem. And you repeat all of this until your formula is either unsatisfiable or empty.
So Alexei,
yeah,
what is the role of that cut set?
Sorry?
The role of the cut set.
The cut set.
Yeah.
So the cut sets are the variables that you have some variable. You have to choose which variable to assign, and the cut set is a set of variables. That you will want to assign in priority. And you want to assign them because once you've assigned all of them from the cut set, from the specific subset, you will have split the graph of your formula. Okay.
Use it so that it results in more components.
Yeah, I will try to give some. I try to give some example after that. Yeah. You are assigning variables that are separator of the primer graph. Okay, so what I've done is that I've looked at two algorithms that differ in particular in this select cut set mechanism. So I've tried to study two families of models of top-node compiler. These are not even like compilers, they are models. Like you can tune a bunch of things. So the first family I call dynamic, and it's supposed to imitate what D4 is doing. Of course, I cannot just reduce the thousands and thousands of lines of code of D4 into 10 lines of pseudocode, so there are some approximations here. The second type of compiler are static, and this would mostly imitate what sharpstat-td, the compiler version of sharpstat-td, is doing. All right. So basically, what I've done is that I fixed the way my compilers are trying to select the cut set, but everything else is basically close to undefined. In particular, once I know which variable I need to assign in priority, selecting which variable which variable in particular really to assign you can make it non-deterministic if you want. It's fine. The result will work. Yeah. Okay. You also have some degree of freedom on how you do caching, because what's done in practice is some syntactical caching. So you really need to find a formula that you've literally seen before to have a cache hit. But you can imagine that maybe in the future, people will be able to do some more clever semantical caching. And so in my result, I've also allowed that the caching be some kind of equivalence check. Like you got two formulas that probably don't look the same, but if they actually compute the same functions, then you will have a cache hit. And so for the processing, that's where I've been a bit lazy. I've just allowed the compilers from a model to do unit propagation or the stronger backbone identification, or they are allowed to do nothing if they want. What's missing here would be close subsumption and vivification. I assume I can add close subsumption without much trouble, but vivification is a bit of a pain to analyze. All right. And I should point out also that in what I've studied, the running time is irrelevant. What I'm interested in is the size of what what the compiler return. How much time it takes to compute it, I don't really care. I do care in the sense that I've used a model that is used in practice, and it's used in practice because it's kind of fast. But after that, you can use any time, any kind of you can do any kind of oracle of non-determinism to for the selection of variable for the processing and stuff like this. Everything you assume is done in O1 time. I'm really only interested in the size of my of the circuits that is constructed. All right, so now for the where the algorithm, so all the algorithm that I studied, they have to differ at least on the cut set selection. So for the dynamic one, the one that imitate D4, selecting the cut set means finding a balanced separator of the primer graph. So the primer graph is something like this. Every vertex is a variable, and you have the two variables are connected if and only if they appear together in a clause of the formula. Okay. And now, how do you find the cut set? So how do you find which variable to assign here? Well, the rule is that you have to find variables that that if you remove the vertex, you will separate the graph into several components, and the component will have roughly the same size. So this is a balance separator. So for instance, in something like that, the compiler could choose. Could say, okay, so B and C form a balance separator of this graph. Once I remove them, which means assigning the variable B and C in any way you want, you would have split your graph, and you would be able to create a decomposable AND gate. So of course, so after you assign B and C in any way you want, you obtain two subformulas, but the graph of the subformula are not necessarily these two things because of the processing and so on. You can assign a bunch of other variables by unit propagation, and really the formulas that you obtain are the primary graph are subgraph of these things. But anyway, all right. So good. So yeah. So for the I don't think so. Is it? Yeah, you have to change your heuristic. Like that? Yes. Good enough? Okay. All right, so for the selection of the cut set in the static case, you use a tree decomposition. So it's static in the sense that the bunch of separator that you're allowed to choose, they are given to you prior to the compilation through a tree decomposition. So I'm not going to introduce what this thing is. So Moshe introduced talk of these things yesterday already. So all right. So that's a tree decomposition of your primer graph, and the way you choose the cut set here is as follows. You look at your formula and you look at the unique highest bag, so like these things that contain variable of your formula, and that will be your cut set. So when you start, you have all the formulas. So the highest bag that contains variables from the formula here would be the top one, and it means that the variable to assign priority are B, D, C, H. All right. So you start assigning some variables, say D and H. Oops. All right, you split your graph. So now you have to empty the cut set, and when you will work on the subformula for this primer for this graph here, you will have to find again your cut set using the same structure you were using, this tree decomposition you were using before. So here, okay, you have this thing. What is the highest bag from the tree decomposition that contains variable from this formula? Well, that's still the same. So the variable to assign priority, according to this selection mechanism, would be B and C.
Just a quick question. So I'm somehow confused. Wouldn't the cut set, isn't it necessary to split all of them simultaneously, or on all variables simultaneously to cut the graph, or you just split on a single variable?
So you're guaranteed that if you assign all of them, you will have split the graph. But it's possible that you will have split the graph before by just assigning a subset of them.
So you have to check that.
You have to check that. Yeah.
Okay, by
Yeah,
subset.
every time. Yeah. So here you were saying you have to assign B. You have to assign B. B and C in priority. Okay. But once you do it, okay, so you end up with a subformula of a graph like this. Again, so now your cut set is empty. You got to compute it again. You have actually not really decomposed your graph. You just the components were basically this thing and that thing, but one of them has been assigned away. And now the cuts, and now what's your cut set? Well, the highest bag that contain element from the subformula now is this one. So here, so now your code set is just going to be A, because B and C are in A, and you will again split your subformula into two parts, and so on and so forth. But you always use the same structure to find which variable to assign next, and that's in this sense that this algorithm is static. Okay. All right. Just to recall, the algorithm that I studied only differ here. So no, they differ at least here. And then all the other stuff, not all of them, but the variable of the selection is they do whatever they want. The cache can be syntactical or semantical. The processing, they can use some unit propagation, they can do nothing, or they can do some backbone identification. No, and so for the results, that the two algorithms are basically incomparable. So there are two results. The first one is that there are infinitely many CNF formulas such that all the compilers that would respect the dynamic model. So when this cut set selection is using this balance separator identification, all the compilers that respect this model, they will create on this instance polynomial size circuits, even the worst one. So that means that you can do the most brainless variable selection. You can have zero processing, and your caching can be the most boring syntactical one. All of them will, all these compilers, they will return polynomial size circuits. On the other hand, all the compilers that respect the static model, so the one using tree decomposition, they will return super polynomial size circuit, actually exponential size circuit, even the best one. So that means that you can have the most clever variable selection you want in the cut set. You can have you can have a caching mechanism that is not just syntactical but semantical, and your processing and your variable processing can be just much more than unit propagation. Doesn't matter as long as they are using the static selection of the cut set, they will create super polynomial size circuits. And you have the other way around also. So the other way around is that you have also, again, infinitely many CNF formulas, such that now at this time it's the static algorithm that will be able to create polynomial size circuits, even if your variable selection inside the cut set is the most stupid one you can imagine. And this time it's the dynamic version that whose compiler will all return super polynomial size circuits, even if you have very clever implementation of the variable selection and of the in-processing. There is, however, one asymmetry here is that this result holds only if you're able to give the 3D if you're allowed to give the 3D composition you will use to your compiler. So that I forgot to say, but you are not allowed to use any kind of 3D composition. To work, you have to assume that you give a close to optimal 3D composition. So ones where the bags are the highest bag in the 3D composition is as small as possible, up to a constant factor. And not all 3D composition will give you this result, but you can feed a 3D composition that will have that will make this separation. All right. Yeah. So I think I'm going to stop here. Sorry. Good.
Thank you. Questions for Alexis? So Moshe, please.
Could you comment what is the implication of this for model counting? In particular, there are model counters such as DPMC that are based on 3D composition. DPMC.
What is it bottom up or top down, this one?
It does a 3D composition,
Yeah.
and then it compiles BDD, or algebraic decision diagram, bottom up.
It does bottom up.
And so what is the implication of these results for model counting, and what will be the relationship between using 3D composition here for model counting and using 3D composition in DPMC for model counting?
Well, that's the thing. For any DPMC is using bottom up, so it doesn't fit in all of these because this was all top down, right? So if you want to compare the DPMC to D4 in a theoretical ways and not just on benchmarks, you have to. I would need to look at the model of bottom-up compilation and do this analysis all over again, because this would only work for top-down compiler.
For top-down, yeah.
Yeah.
Okay.
So unfortunately, what I can say is nothing basically, and as long as I've not done this comparison, I don't have any.
Let's follow up on that.
Okay. Sorry.
Oliver?
A specific question regarding the heuristical approach of these of the algorithmic scheme you showed. So it seems the main focus is on variable disjoint splitting. So that's where you are aiming at. But so now I observed excessively bad runtimes of D4 on my of all of these algorithms on my instances based on Latin squares, which naturally there is nothing there. So you can never have any variable disjoint splitting there. It doesn't exist at all. And then and then it's much worse than ordinary, let's say, DPLL style heuristics, which go actually for the splitting variable, set a variable true and false, minimize the trees. So would this would you also cover such algorithms with your scheme, so which so just go for the variables, not and split so that the tree sizes on the left and on the right are as small as possible? While you completely forget, let's say, about the variable disjoint splitting.
I'm not sure I'm following the question. So
the heuristic scheme is extremely narrow, as far as I understand, because you only focus on one target. Go for the variable disjoint splitting.
Yeah.
But you don't minimize the tree sizes as an ordinary DPLL. You see, so you're on the left, and you split. Your splitting algorithm produces a subtree on the left and on the right.
Yeah.
And you could just minimize the tree sizes. So that's the heuristics, the usual heuristics which a DPLL solver. Namely, if I have an ordinary DPLL solver on this Latin square problem, is very fast. While all of these D4 and so are unbelievable slow.
So you could do a similar kind of comparison. So you would need you would basically compare this kind of algorithm, which strategy is a split at all cost, to another model where you don't have this cut set selection and you directly go for the variable selection. However, here you would need to, for having some interesting results, you will need to put some constraint on the variable selection, because here I'm allowed to do variable selection non-deterministically inside the cut set. But the constraint is the cut set constraint is already hard enough. If you can just select any variable non-deterministically, then you will probably the algorithm will just by theory, return the best compiled form possible. So to really say something meaningful that would encompass the behavior of the algorithm that you're using, you would still need some. You would need to get rid of the cut set mechanism, but you would need to replace it, I feel, by some model of your variable selection heuristic, and it needs to be a model. If it's just one specific heuristic, maybe it's not so interesting, and you would need a family of heuristic that you would compare.
Thank you. Yes, great. Thank you.
Okay, so let's thank Alexis again. And the final talk of the session is on the relative strength of sharp-sat proof systems. And the talk is going to be given by Tim.
Yeah, thank you. All right, so yeah, our paper analyzed the relative strength of sharp-sat proof systems. And that means that we basically compare how the existing proof systems relate to each other. And I will go briefly for the problem setting. So we always assume that we have some formula phi, and that is the formula we want to count on. And this formula is always given as CNN. And then the sharp-sat problem, or also model counting problem, is a generalization of SAT, where we do not only want to know is there at least one satisfying assignment, but we want to know how many such satisfying assignments or models are there exactly. And this problem is complete for the sharp-P complexity class. And to give you an idea how big this class is, there is a very famous result from Toda that states that any problem in the polynomial hierarchy can be solved in polynomial time if we have access to a sharp-P oracle. And that indicates that under common assumptions, this class sharp-P is really much bigger than NP, and in particular that the model counting problem seems to be much harder than SAT. Okay, nevertheless, there are quite a few applications in reword, as we already heard here in this conference. Yeah, just to name some others, it's in probabilistic reasoning, in risk analysis, and also some fields of AI. And this is simply because we can encode many problems very naturally and in a very succinct way with model counting. And this is also the reason why people started to design algorithms for that. And one could argue that somehow the interest in this problem also increased over the last maybe 5 to 10 years, I would say. So there are very different approaches how to deal with this problem. And yeah, some of these approaches here may overlap, but okay. And there's also a model counting competition here at this conference since 2020. Yeah, but this is all only the practical point of view. We in our paper consider this in a more theoretical we have a more theoretical focus, and for that we use proof systems. And yeah, a proof system is a very general framework that can be used for many problems or languages. But if we apply it to model counting, then a proof system has to satisfy 3 properties. First of all, it has to be sound. That means that if we have a proof that a formula has C models, then this is correct. Secondly, we have completeness. That means that for every formula, we really have a proof in our proof system for that formula. And the third point is that there has to be some way how we can verify proofs efficiently. And efficiently means that this is possible in polynomial time. Okay, so why do we care about proof systems? Why should we study them? And as we heard already quite often in this conference, it's very crucial for enable us to do proof logging. That means we want to have a proof system that is really strong enough such that we can basically translate any step a solver performs on some input into our proof system, and then basically have a proof when the solver finishes, which we can verify again. And so we have some kind of guarantee that the solver really handles our formula correctly. Also, a second point that is quite interesting is that we can gain some insights into our performance of the solver. Because if we have a proof system that is strong enough to extract these proofs efficiently, but is still somehow weak enough that we can show lower bounds, then we can use these lower bounds to require to obtain lower bounds on the running time. Yeah, because if some phi has no short proof in our proof system, then we can immediately conclude that the solver won't be able to handle this formula well. Okay, and if we have a look at the situation in SAT in this regards, then we see that there are really many different proof systems, and yeah, they are very different, and we know many connections between them. We know how many of them relate to each other, and we have very many theoretical results there. On the other hand, the situation is very differently in sharp SAT. And that is, we have actually only 3 proof systems yet, and they all occurred during the last 5 years. And that is, we have KCPS, which is a static proof system, which is based on knowledge compilation. Then we have MICE, which is the only line-based proof system we have for model counting. And then we have CPOC, which is a bit similar as KCPS, but in somehow a more general setting. And yeah, they all were introduced at the SAT conference, actually. And they were also all somehow designed for proof logging. And the situation is a bit strange because all these 3 systems were introduced, but we do not really know how they relate to each other. So their relation is completely open. And yeah, this leads us to our paper, because our main contribution is to answer this question: how do these systems relate to each other? And we were able to basically provide the full picture for that. And this can be summarized here in such a figure. We see that MICE and KCPS are incomparable. That means then that on some formulas, MICE is exponentially stronger. On some other formulas, KCPS is exponentially stronger. And CPOC is better than both of them. Yeah? And in fact, CPOC simulates both systems and is also exponentially separated from both. And yeah, in fact, our contribution is a bit more. We also introduced 2 new systems that are slight adaptations of existing ones. That is, for one, KCPS Plus, which is a generalization of KCPS. And also the CPOC on decision DNNFs is basically just a restriction of CPOC. And these 2 systems very well into this figure here. Okay, and now for the rest of the talk, I want to give you brief introductions to the different proof systems and want to sketch some main ideas of the simulations and separations.
Just ask a
Sure.
quick question. The C, the representation of the C, does that matter? You could consider unary, binary, or even more compressed versions for C. So making distinctions for very large counts, but you don't consider that.
Did not consider
Okay.
that. Oh. Okay. Yeah. So we start with introducing KCPS, and for that we need these decision DNNFs, which you already should know from the previous talk. So this is just some circuit class where actually one of the properties that is easy is counting, which why it is used for model counting. And we consider a restricted version of decision DNNFs, that is, we look at certified decision DNNFs. And yeah, basically we want that every 0 gate in our decision DNNF is certified. That means that it is labeled with some clause C. This clause has to appear in our formula phi, and every path that leads to this 0 gate has to falsify this clause. Yeah, if we have a look at a small example here, then we consider really a very basic formula here with only 2 clauses. Then this is a decision DNNF that represents this formula. And then we can have these 2 0 gates. And in order to be a certified decision DNNF, we have to find certificates for these 2 gates. And yeah, here it is really easy, because if we have a look here, we only reach this 0 gate if we make C false and D false. And therefore we can label it with this clause, because only this one assignment leads here, and it is false. This assignment falsifies this clause. And a similar thing here. And yeah, and yeah, in fact, we can really just compute the model count here very easily by computing it upwards. So now with this in mind, we can introduce the KCPS proof system, which was introduced 5 years ago. So it is the first proof system for model counting. And the idea is that a proof basically just contains one certified decision DNNF, and this is the whole proof, because this decision DNNF implicitly also contains the model count, because we can simply compute it from the decision DNNF. And in order to be a proof system, we have to make sure that we can verify this proof efficiently. And in particular, we have to make sure that this equivalence of D and phi can be computed efficiently. And for that, we have to show both directions separately. And the one entailment that D entails phi can always be checked efficiently in polynomial time. This is again just a property of decision DNNFs that we can exploit to do that. So we do not have to care about this direction. The other direction that phi entails D, on the other hand, is for arbitrary decision DNNFs NP complete. So this is a very hard problem usually. And this is the reason why we use these certified decision DNNFs, because if we can use the certificates, this direction also becomes easy. So we have, we can always check this equivalence efficiently on these decision DNNFs, and therefore this is sufficient to be a proof for the formula. Okay, so this was KCPS. Now we introduce mice. This was introduced 2 years ago and was simplified by us last year. And we will refer to the simplified version here. So as I said, it's a line-based proof systems, and the lines are called claims, and every claim is just a free tuple. And this free tuple contains a formula F, which is just a set of clauses of phi. Then we have an assumption A, which is a partial assignment of the variables that occur in this formula F. And we have some number C. And this claim then states that the formula F under the assumption A has exactly C models. And if we can do that, our goal is to derive somehow this claim, because if we can derive this claim, then we know that the formula phi has exactly C models, and we are done. So the interesting thing is, how can we derive these claims? And for that, we have 4 different rules here. First of all, we have an axiom rule, which is just a rule we usually start a proof with. Then we have an extension where we can make our formula a bit larger. Then we have composition. Composition uses different claims that all consider the same formula, but under different assumptions. So if you want, these assumptions basically are some kind of case distinction. And if they are a complete case distinction, then we can make our assumption weaker and simply sum these counts up. So as intuition. And finally, we have a rule that is called join, which takes 2 claims and basically combines them. So if the formulas in the claims F1 and F2 are somehow independent, so they do not share any variables, then we can just put these formulas together and multiply the model counts. So this is a very brief intuition for this proof system. And there are already some lower bounds for both systems, because we know that there are formulas that require exponentially large decision DNNFs, as we heard in the previous talk. So these formulas obviously also have large KCPS proofs. And we also have an exponential lower bound for mice, which was showed last year. However, the relation between these 2 systems was not clear before, and I think it's also not obvious because the 2 systems are very different in some way. And this is our first result. We showed these are incomparable, so there are exponential separations in both directions. And I want to sketch the first direction. This is actually the easy one, because we want to show that there are formulas that are easy for mice, but hard for KCPS. And for that, it is sufficient to have a look only on unsatisfiable formulas, because it's not too difficult to show that KCPS is equivalent to regular resolution, which is a restricted version of resolution where we are only allowed to apply resolution over over a variable once in one path. And mice, on the other hand, is equivalent to resolution on unsatisfiable formulas. And there are many results that show exponential separations between regular resolution and resolution. So this is just one of these results. There are others. And if we just stick these things together, then we immediately obtain this result that mice is on some formulas exponentially stronger than KCPS. Okay. So next, we show the other direction. This direction is a bit more involved and more difficult because we need some CNF that has a short decision DNF. Oh, sorry, short decision DNF representation, but requires large mice proofs. And in particular, we need some lower bound for this mice proof system. And so far, we only have one lower bound from last year, but this lower bound is somehow, this relies on formulas that have large decision DNF size. So we cannot really use these lower bounds, and we need something new here. And yeah, the very, very high level idea is that we use formulas similar to the Pepling formulas that were used to separate tree-like and general resolution. And we can slightly modify them and get some separation here. But the proof is more technically involved, so I will skip this here. This is unsatisfiable formulas. Yeah. Yeah, on unsatisfiable formulas, mice is always just better because mice is equivalent to resolution and therefore always better than regular resolution. Okay, then now we go this figure up and we get to KCPS plus, which is a generalization of KCPS, where we do not require our certificates to be clauses that appear in our formula phi directly. Instead, we allow that we can derive this clauses with resolution from our formula phi. And yeah, this idea is not new. It was already mentioned in the original KCPS paper. So we just wrote it up. And yeah, now this system obviously is as strong as resolution on unsatisfiable formulas. So the whole idea for this separation between these two systems does not work anymore. And in fact, we can show that there is no separation at all because this resulting system here simulates mice. And it also simulates KCPS. But yeah, this separation that KCPS plus simulates KCPS is by definition more or less. So we only have to show this left arrow here. And the idea is that we can start with some mice proof for some formula phi, and we basically can somehow translate this formula, this mice proof into a decision DNF for phi. And this is also something we showed already last year. And all we now have to do is that we can show that we can make this decision DNF also certified. And this is again a bit more technically, but this can be done. So this result is basically just a generalization of our result last year. And with these two simulations, we immediately also obtain the exponential separations here, because we know there is some formula, for instance, where mice is hard, but KCPS is has short proofs. Then immediately we can obtain that KCPS plus also has short proofs because it simulates KCPS, and therefore we obtain a separation between KCPS plus and mice. And we can do the exact same thing for this separation here. So, okay. Go one more step up, and we get to CPOC on decision DNFs. And the idea is very similar to the idea to KCPS, because we want to have as proof only a decision DNF that is equivalent to our formula phi. However, we do not want to restrict ourselves to these certified decision DNFs anymore. So we want to get rid of this restriction. And as I told, the certificates were only used to show that this entailment is indeed true. Yeah, so with these certificates, this check is always possible efficiently. However, the new idea here is that we simply add a proof that this is indeed true with resolution additionally in the proof itself. Yeah, because if we add this to the proof, then we can obviously always check this also. And yeah, so this is a restricted version of the CPOC system, but this version was already implemented in their proof checker last year. And they also argued that this system is sufficient to do proof logging for all the current solvers that are out there. Yeah. And now we can show that this system simulates KCPS+. And the idea is, again, not too difficult because in a KCPS+ proof, we have already some certified decision DNNF. And this decision DNNF can just be reused for the CPOC proof. And then we only have to find a resolution proof that shows that this is indeed true. However, the idea was that the certificates were used that this can be computed efficiently or checked efficiently. So all we have to do is we have to show that we can also check this or prove this efficiently with resolution. So this is a bit more technically, but I think the intuition should be clear. Finally, we want to go to the top field here, and for that is CPOC. And CPOC is very similar to the CPOC on decision DNNFs. However, we want to make this circuit class, this decision DNNF, somehow stronger. And yeah, so basically the idea is we want to make it as strong as possible. And then the resulting system seems to be this POC circuit class. Partition-oriented graph. So this. Oh, sorry. Yeah, it's a typo. Yeah. Yeah, I'm not sure. I think this also is a new circuit class. It was not mentioned earlier, but it was under this name in the literature already. So just a deterministic decomposable circuit. So it's basically like the DDNNF we heard before, but without the negation normal form. Yeah? We can have NOT gates anywhere. So it's a circuit we have still the leaves are 0, 1 or variables. And we have the AND gates that are decomposable OR gates that are deterministic as in DNNFs. But now the new thing is we also have these NOT gates. And intuitively, this is somehow the largest class where we can still count on efficiently. Okay. Now we can define the CPOC system. Here it's correct. Certified partition-oriented graphs. And again, the idea is the very same. We want to have in a proof simply this circuit, and this time it's a POC. And now we have to add some more stuff to the proof because all these properties of the POC and the equivalence are not trivial to check anymore. So we have to provide additional resolution proofs that the OR gates are indeed deterministic. We have to give a resolution proof that phi entails P and also one that P entails phi. So these two are needed also for the equivalence, and this one is needed to somehow check that the POC is indeed a valid POC. So this is some kind of trade-off. We make the circuit class much more stronger, but we have to provide more proofs here. And yeah, this seems to be a very strong proof system because we do not know any lower bounds yet for the system. And by definition, we can see that CPOC simulates this CPOC on decision DNNFs, because if we choose a decision DNNF as such a POC, then this property here becomes trivial, and also these this proof here becomes trivial, and only the one resolution proof we also need in this proof system, CPOC on decision DNNFs, remains. Okay, and this basically finishes our complete picture here. So this is the result from our paper, and I hope you have a nice intuition, or a brief intuition at least, how these systems work, and yeah, how these separations work as well. And yeah, so here's a summary again, what we have done, but I think it was already shown in the picture before. Maybe one last thing, I think maybe that also these two proof systems that we formalized here might be interesting to look at for further research, because they seem to be very interesting somehow, because KCPS has this weakness that it is just regular resolution, so this might be not too interesting, and this is a very, very natural extension of it. And also this CPOC on decision DNNF might be interesting because it is sufficient to model, to extract proofs from current solvers, and these negation gates that are added into the circuit class have some strange behaviors, I think. Yeah, and that's it. Thank you.
Questions for Tim? Get a mic back in the...
Can I ask a question?
Yes, go ahead.
So if you look at DPMC,
Mhm.
it doesn't describe explicitly a proof system, but there is an underlying proof system, which is you take the concept of BDD proof for satisfiability from Matseres et al., and instead you get ADD proofs for counting. And in fact, because the dynamic programming algorithm, it automatically produces the log is the proof. Just the evaluation structure is the proof. So have you looked at all to look at ADD proofs and how they compare to these proof systems?
We have not looked at other proof systems yet. We wanted to have a closer look at many different solvers and how they work, and try to somehow tailor proof systems exactly to fit how strong they are. So in this case, it would be very easy, but we also wanted to do this for other solvers maybe, and somehow design these proof systems such that we can compare them also to these systems and get some insights.
What we know, for example, BDD proofs, they are stronger than almost all the standards proof system for satisfiability.
Okay.
They're stronger than resolution and cutting planes. They're very strong proof systems.
Okay.
So it will be really interesting to look at ADD proof system for SharpSat.
Okay, yeah, we will do this. Thank you.
Can you comment on CPOC strength when dealing with unsatisfiable formulas?
CPOC unsatisfiable formulas?
You said KCPS was equivalent to regular resolution, right? When dealing with unsatisfiable formulas. Can you comment on strength of CPOC when restricted to unsatisfiable formulas?
This is a bit a strange system then, because we only use resolution proofs here. However, it might still be a bit stronger than resolution, because we can use this POC to introduce some new variables, some extension variables, but they are not completely arbitrary. So we cannot do extended resolution probably, because these variables that we introduce have to satisfy these deterministic and these properties of the circuit. So it's a bit strange, but I think we are slightly above resolution.
Do you have
probably,
like any upper bounds for formulas that are hard for resolution, but that CPOC can do?
I mean, it can't be stronger than extended resolution, I think.
Yeah, no, but you know, one of our favorite formulas, I don't know.
We've started to look at it, but the system is really, really strange. But yeah, it's also one open questions that we want to investigate further.
Okay, I see. And Oliver?
I could imagine that considering unary C, unary count makes a certain addition because in this way you would concentrate on small counts. Possibly it's somewhat trivial also, but in my mind, so small count could show up, not just binary, not just usual binary representation.
If we have unary count, it might be somehow that we get down to propositional, to the start hardness somehow, because
is it not? It could be. Yes, I was also thinking about that. Possibly it is just then a splitting into when you prove each is unsatisfied otherwise.
Yeah, because in mice, for instance, we could just derive that the models every one by one, and then do one step that shows there are no other models. So these proofs at least have always small number of claims. So I'm not sure if this is too interesting, but yeah, it's still quite nice.
Okay, so with that, let's thank Tim again and all speakers of this session.
Thank you.
I don't know if there are any announcements before we're heading out for lunch. Oh, one announcement. Suspense is enormous. So we're waiting for a microphone, maybe. Yes.
Few announcements. Of course, the usual announcer is not there because he's trying to sort out some of the issues, or well, he's trying to sort out the important financial matters. So I thought I'll take his place and make a few announcements. The first of which is that I'm sure that I do not need to announce the usual announcements that you already know. So I shall leave that out, which is about photographs and beverages and so on. The second most important announcement is that we have been seeing and listening to and learning about proof certificates since the morning. A lot of learnings have been happening. So we thought of actually taking all those learnings and implementing them via actual certificates, actual proof certificates of our appreciation for the people who are helping out in various ways in making these sessions happen. So as you would have seen through the course of the conference and the workshops and the school, that there are these student volunteers who are running around, setting up the slides, the mic, the mouse pointer, getting the speakers do a little dry run of their talks, the camera, the audio, and a lot of things that are happening, backstage. If many of these are people from our group at TCS, it is also the case that many of them are students from across the country who have come just to attend the conference, but they have been more than gracious in offering themselves, for helping out with various activities with respect to the organizational works. Yeah, so they have been just coming up and saying, okay, is there something that I can do for the conference? Is there something that I can do? So it's been great, and so with all this, involvement from their own side, it has become much easier to get things, make things happen for the session. So as a little token of our appreciation for all the things that they have that they are doing, we would like to give them actual proof certificates. And to be able to do that, I would request Moshe, if you could, if they could receive these certificates from you. Okay, so I'll be just calling out the names, and the people who are there, yeah, they should come and get the certificate from Moshe. We will first begin with the students who are coming from, not from our group, but from across the country. Okay, and we'll begin with the youngest member, who is an undergraduate student from VIT Vellore, and she has been there since the beginning of the events, since the beginning of the week, and it's been just great that she has been involved in such a big way. So I would like to call upon Nidhi Gunjal to come on and get her certificate from Moshe. Oh, there? Okay, on. And just as enthusiastic as her is her partner in crime,